Hello and welcome to our webinar of section 1.5 infinite limits, and this is of the examples that we have. And so basically what we're looking at here is they're asking us to graph this function and find the limit as x approaches 2 from the right hand side, 2 from the left hand side, and then what's happening overall. And this is kind of a summary of what's happening in this section. If we have the limit approach from the right hand side, you can see that we end up with it from the positive values. You can see that my y is going without bound. So previously we said it doesn't exist, but now we're going to say it goes to infinity. On the left hand side, as we're coming from the negative side, you can see that my y decreases without bound, and therefore we go to negative infinity. Since they are not approaching the same value, this still does not exist. Okay, this does not exist. There's no limit for this. But what we're changing in this section is that if I have both of them approach the same infinity, the positive infinity in this case in my drawing, as they go up from the left and from the right, we can say instead of it does not exist, we could say it's infinity for the last one. So from the left it was positive infinity, or from the right it was positive infinity, from the left it was positive infinity, therefore we can go to positive infinity for the third one. So that would have been like A, B. And so then the other way, if they both go down, same deal. But if they're going opposite directions, it still doesn't exist. Infinity really isn't a number, but we're just kind of using it as one in this case. So then we want to determine the limits for the graphs, and so we're looking at these graphs down below. And so if we're asked to find the limit of 1 over x minus 1, then we would go ahead and just look at the graph of it, and you can see that from the left and from the right we are approaching different values, so this one does not exist. From the left we are approaching negative infinity, from the right we are approaching positive infinity, and so we go positive infinity from one side, negative infinity to the other, therefore it doesn't exist. They're going to different values. The second one, though, you can see this was graph A, this one's graph B, and you can see that they're both going up as we approach 1. They're both going up to positive infinity, and I just graphed these on my graphing calculator. And since they're both going to positive infinity, we'll say that's positive infinity. This guy, from the negatives, we are going to positive infinity. From the positives, we're going to negative infinity, so this one does not exist. And then this guy right here, they're both falling down the page. This is what I was just talking about, both going to negative infinity. Since they're both going to the same spot, we can call it negative infinity instead of a number. But that's basically what we're talking about. So then this brings up the conversation of vertical asymptotes and where do they appear and how do we find them. So for example A, we are given the function 1 over 2 times x plus 1. Well, if that's our function, if that's our f of x, then how do we find a vertical asymptote? Well, we fall back on our algebra 2. When the bottom is 0, that's where vertical asymptotes appear. So if I say 2 times x plus 1 equals 0 and solve for x, I find out that x is negative 1 where it doesn't exist. So our vertical asymptote is at x equals negative 1. So then for the next one, same idea. You can see I graphed them for B. For B, we have the function down here. This was A. This one's B. And so if I graph this function, if I say f of x equals to x squared plus 1 over x squared minus 1, well, the top is not factorable, so I just leave it as it is. The bottom I can factor and say x plus 1, x minus 1, and you can see that at this case the vertical asymptotes appear when we are at 1 and negative 1, when x is 1 and negative 1, and that's basically setting the bottom equal to 0 and using our zero product property from algebra 2. Then we get to the cotangent of x, and so I'll move down here, down below for that one, and so the cotangent of x could be written as cosine of x over sine of x. And so this is the trick to this one. In order to find out where the vertical asymptotes are, in this case, we have to know where sine of x equals 0. And so then wherever sine of x equals 0, then that is what we're talking about. So we have vertical asymptotes at 0, and at pi, and at negative pi, and so that's basically where our vertical asymptotes appear. And so it's all the values of 0 or pi that would show up in our graph, and that's what vertical asymptotes are. So it works for trig functions, it works for all of our functions that we're dealing with. Our next example is they want us to find out where the vertical asymptotes are in this graph. And, well, first of all, I would set the bottom equal to 0. But if you look at my graph, it looks like for the bottom should be x plus 2, x minus 2 when I factor it. And when I factor it, I can see at positive 2 here, I don't have a vertical asymptote. I bet there's something going on in the graph there that I can't see. So let's factor the top and see what's going on. If I factor the top, I get x, let's see, x plus 2, x minus 2, x plus 4. Let me go back and change that sign here. X minus 2. So I get x minus 2 and x plus 4. Because that will give, that's my factoring of this up here. And you can see at x minus 2, those terms are in common. When x is equal to 2, that's what it would, when I set x minus 2 equal to 0, I get when x is equal to 2, there's actually a hole in the graph. That's a removable discontinuity that we talked about in the previous section. In this section, then, that x is equal to negative 2 is our non-removable, and the non-removable discontinuities become vertical asymptotes, which is really what we're looking for in this case. So there's a hole in this graph and a vertical asymptote also. This guy is not what we're looking for. This one is. But we need to, we'll talk about those when we deal with this stuff a little bit more. Talk about the holes in the graph. So then we have a graph that looks like this, and they want us to find the limit from both sides. And so if I find the limit as we approach 1 from the negative side, we're approaching 1, the x values of 1, what's happening to my y? Well, you can see I go to positive infinity. This guy over here, as I approach the x values from the positive side, you can see my graph falls down the page and goes to negative infinity. So the limit, for the limit of this graph itself, the limit as x goes to 1 of x squared minus 3x over x minus 1 is actually, does not exist, but each part is done separately, and we can have a limit for those. So then we get to something that's like this, and this follows our properties of infinite limits, and that's just from your notes, so make sure you get that down. But from our properties, we're saying that in this case we're taking 1 and adding it on to infinity, and then so we would say 1 plus infinity, which is really just infinity. So all those little kid arguments that you had when you were a kid that said, you know, infinity, infinity plus 1, those kind of arguments, you know, to one-up somebody, those aren't really true because they're just infinity, because infinity is a concept, and if you want, we can talk more about that in class. In this case, we have a limit as x squared plus 1 equals 2, and the cotangent is negative infinity, so really this limit, when we do it as a division problem, becomes 2 over negative infinity, and since 2 is kind of small in comparison to infinity, if we take a number and divide it by the smallest negative number you can think of, you're going to end up with 0, because once we divide by this really negative number, if it was positive infinity, you'd still think of it as 0 because you're taking 2 and dividing it by a really large number. Well, 2 divided by a really small negative number, would give me 0 also. And so then our final one down here, we're taking 3 and multiplying it by the cotangent of x, and we're finding the limit. And so we have the limit is 3 and the limit is infinity, so we really have 3 times infinity, which doesn't change the infinity at all, and so we get infinity for that limit. And so these are just our properties of infinity, and make sure you check them out. They're on page 87 in your math book. So that completes the examples for this unit, and I hope you guys